Hello guys, welcome to quantum control lectures. This would be our sixth lecture in the series. So in the last class we were talking about a new kind of angular momentum corresponding to the half integral values of J. So before moving further, I want to introduce a new notation for this half integral angular momentum. So the total spin angular momentum would be denoted as s hat squared, and the z component of the spin angular momentum would be given as s sub z, and we denote the state which corresponds to s z eigenvalue of plus h bar by 2 by this state, okay, and minus h bar by 2 by minus half. So to develop the theory of spin angular momentum, we have to define a two-dimensional Hilbert space spanned by these two states, that is plus half and minus half. Next, we have to realize that direction z is defined by us. It's not a sacred direction in physical 3D space we live in. It is just the direction where the magnetic field strength goes from high at North Pole to low at South Pole. We might have called it x or y direction. It does not have any consequences on the experiment. So this means that x component of the spin angular momentum can be written like this, and the y component can be written like this, okay, and they behave exactly the same way as the s sub z operator. By this I mean that this operator, when operating on this state corresponding to plus minus h bar by 2 eigenvalue, it gives us plus minus h bar by 2. This is an eigenstate for Sx operator. Similarly, this would give us operating on the plus minus half state, and obviously the Sz would also give this. That is why this eigenvalue equation. So this will help us to evaluate the effect of S squared operator on this states. We know that S squared operator is defined like this. The effect of the S squared operator on this state, Sx squared, this would be equal to this plus z whole squared plus minus half. So this is equal to plus minus h bar by 2 or 2 times, because we are applying this operator 2 times, plus minus bar by 2 whole square plus minus half plus minus h bar by 2 minus. So this is equal to, we can rewrite this as this is squared, so this plus minus would disappear, and this would be equal to h squared by 4 plus h squared by 4 plus h squared by 4, and the state plus minus half come out, and this would be equal to 3 by 4h squared. So this is the eigenvalue equation of this operator s squared. So any state in this two-dimensional Hilbert space in general can be written as linear combination of these two basis states, where alpha and beta are complex numbers. So in order to qualify as some kind of angular momentum, recall that the Sx, Sy and Sz operators need to satisfy the angular momentum commutation relation, and you can check that very easily by investigating the action of commutators of all possible combination of these three operators, that is of between these three operators, and see its effect on the state plus minus half. You can compute this very easily, and you would find that they satisfy the same commutation relation as satisfied by the generalized angular momentum, and it is sort of expected because it was evaluated from the generalized angular momentum, because it is specialized angular momentum corresponding to half integral values of J. So therefore the same analysis can be made as made in the case of generalized angular momentum, and similarly we can define the raising and lowering operators as s plus hat, similar to generalized angular momentum, as this. So one thing you should know, the value of small m, that is spin value, so it is plus half and minus corresponding to the value of j half, and we denote the m for spin angular momentum as m sub s to distinguish between our integral angular momentum and half integral angular momentum. Okay, as m sub s and j corresponding to half integral values as s. Therefore the complete notation for the state for the spin angular momentum would be this. Okay, that is, so since s is same for both the state, we sometimes drop this and only write the m sub s value. So we also know that as effect on ms would be similar of j plus on j m of state, which is this h bar s k and s minus s s and s, and operating on this state should give us 0, because you cannot go higher than plus half eigenvalue. There are only two eigenvalues corresponding to plus half and minus half state, so this obviously should give us 0. So if you put this value of half in this expression, you should get equal to 0, because the s is half, ms is half, and this first term would make the entire RHS to go 0. This is half, it doesn't matter what this is, because this thing is going to make everything 0. So this is 0, and this is obviously s minus similarly can be written as this, cannot get lower than this, again 0. So for later use I need the expression of Sx in terms of S plus and S minus, which is given like this. Okay, you can evaluate it very easily. This is iota. So since the Hilbert space corresponding to spin is finite, and that too only two-dimensional, the operators operating on it are very well amenable to matrix representation in this plus half and minus half basis. So the next topic would be the matrix representation of all the operators Sx, Sy, Sz and S squared, and also S plus and S minus, all the operators, its matrix representation. So in this half and half minus half basis, we can write any arbitrary spin state. As I have stated earlier, any spin state psi can be written as a linear combination of these two states. That is, they span this two-dimensional Hilbert space. This alpha and beta are complex. So if we choose this two states as a standard basis, that is half and half as 1 0 and half and minus half as 0 1, this would give psi as simply a column vector having alpha and beta as an elements. So suppose there is any operator in this acting on the vectors of this two-dimensional Hilbert space. We denote that operator as O, and it acts on this general spin state psi, which we drop the half s value because it is same for both the states, and let us operate this operator on this, which would mean that this, and let us denote this state as psi prime, and we wish to obtain the state psi in as a column vector of two complex numbers C1 and C2. C1 and C2 are complex numbers. This implies that psi prime can also be written as linear combination of these two operators, and this means that C1 is nothing but the inner product of this state plus half with the state psi prime, okay, which is equal to half psi prime is given like this, and this is equal to alpha comes out because it's just a scalar. Similarly, similar thing can be said for the coefficient C2, and which is equal to the inner product of minus half with psi prime, and it is given like this. Therefore psi prime can be written as, which is, we have denoted it by a column vector having elements C1 and C2, and we have evaluated these expressions for C1 and C2, and let us substitute it over here. This would give us expression for C1, and this would be alpha minus half. So if you note that this thing is can be written as multiplication between a matrix and a vector like this. Note this, these two are same, because if you multiply this matrix with this vector, you would get this vector. If you note, this is nothing but the vector representation of the state psi, the general spin state, and this is nothing but the matrix representation of this any arbitrary operator O acting on this two-dimensional Hilbert space. So this implies that any operator operating on this 2 by 2 Hilbert space can be written as 2 by 2 matrix, like as we have written over here. This means that we have to only determine the elements of this matrix for operators like s squared, sx and sy and sc. So let us calculate them one by one. So matrix for s squared. So you know that the effect of x squared on this plus half state is this eigenvalue comes out, and if you assume that the plus half and minus half state are orthonormal, this would give us this, and similarly this half s squared minus half would give us this 0, because this 3 by 4 s squared would come out, but these two states are orthogonal, their inner product would vanish and this would be 0 again. Therefore this thing, but also this element will also be 0 for the same reason, and this state, this element would again give us h square. The matrix for s squared is given by 3, h bar squared by 4 is 1 0 0 1, that is, this is an identity operator. 3 by 4 s squared identity matrix. So matrix for s set, first element would be this h bar by 2 would come out, because this is the eigenvalue of s set when operating on this state, plus half, and this half would give me 1 because they are assumed to be orthonormal. This would be the value of this element, s z minus half. So this is minus h bar by 2, but this two states are orthogonal to each other, so it would make this element go 0. Similarly, by the same argument, this element is also 0, and this element would give us minus half, minus half would give us minus h bar by 2 would come out, and this inner product between minus half and minus half would give me 1, and this h bar by 2 would be the value of this element. So this matrix of SC would be given like this: 1 minus 1 0 0, and this matrix has a special notation given by like this: sigma sub z. So similarly, we can calculate for the matrix for S plus operator, which is given like this. This first element would be this, and you know this S plus kills this state plus half, because you cannot go higher than this state plus half, and this would be 0. And similarly, this half S plus minus half would give us this h bar is the eigenvalue of this operator operating on minus half, and it raises this value to half, and we have over here another half, and this h bar would come out, and half inner product is 1. So this value h bar is the value of this matrix element. You can just put it over the value of the this minus half and the expression for this eigenvalue equation involving s plus and minus half. Okay, so you would get this h bar. So next would be half s plus half. So again this s plus would kill this plus half state and this element will go to 0. And so the matrix representation of this would be 0 1 0 0. And again this matrix has a special notation, that is sigma plus. So again this matrix for s minus is there when the first element is this. So if you apply this expression for s minus, that is put half in the expression for the eigenvalue of this equation s minus, applying on this plus half state, this would be this half minus half plus 1 h bar. Lower the value by minus half and this would be 0. Okay, this value half s minus minus half be 0 because this you cannot get lower than this state minus half. So this would be again 0. This state minus half would again be 0 for the similar reason. And but this state would not be 0. This minus half s minus plus half element would not be 0. This would give us h bar half this minus, because it would lower this value of plus half to minus half. This would be h bar. So the matrix corresponding to this operator as lowering operator s minus would be h bar 0 0 1 h bar by sigma minus. This is again denoted by a special notation sigma minus, where sigma minus is this. So we can now obtain the matrix for Sx by simply substituting the matrix for S plus and S minus in this expression which I have written earlier. And this special matrix is denoted by sigma x, and Sy it was written like this: S plus S minus by 2 iota, and this is equal to h bar by 2 iota 0 1 minus 1 0. Multiply this numerator and denoted by iota and take that iota inside. This would, the sign would get reversed. This operator is denoted by a special notation called sigma y. So this is this sigma x, sigma y and sigma z are called Pauli's spin operators. Now time has come to introduce the next postulate of quantum mechanics, which is the postulate 4 of quantum mechanics, and it is called the projective measurement postulate. The statement of this postulate is: if the quantum measurement is described by a collection of projection operators, which is like this, and the set of indices, this m r represent the set of outcomes of some observable or the dynamical variable m and its corresponding Hermitian operator m hat. Further, if the pre-measurement state, that is the state of the system before the measurement of this dynamical variable m, is given like this xi, then after measurement state would change due to the act of measurement, and that post measurement state is given like this: the projection operator operating on xi divided by the expectation value of this projection operator, and the probability of outcome m and the post measurement state of this is given like this: the expectation value of the projection operator corresponding to the eigenvalue m. This is the probability that measurement value would be small m of the variable m which we are trying to measure. This is what the postulate 4 says. And obviously, since we know that if I sum this of over all possible values of values small m of the variable capital M, this is equal to 1. This implies that the the sum of all the projection operators should give me the identity operator. Because if we assume that this xi are and normalized, then this is given like this, we can take this summation inside this bracket, okay, and this has to be equal to 1. This only can happen if this thing inside is identity. Then because then identity operating on this state would give me again xi, and psi and xi are equal to 1. So the requirement of conservation of probability gives us this requirement on the projection operators. Okay, so we can now, as an example, as an illustration, explain the Stern-Gerlach experiment based on this postulate. So the projection operator corresponding to plus h bar by 2 eigenvalue can be written like this: plus half, this is the projection operator corresponding to the value plus h bar by 2, and projection operator corresponding to minus h bar by 2 is given like this. And we assume that pre-measurement state of the system was some arbitrary linear combination of these two spin states, where this a and b are complex numbers. So the probability of having the eigenvalue plus h bar by 2 is given like this according to the postulate, and if you calculate, this is the magnitude squared of complex number a, and probability minus half, and it is given like this. Suppose the atom is found to have plus h bar by 2 spin by virtue of being observed on the upper side of the screen, then the post measurement state would be plus half xi according to the postulate is given like this. So this is plus half, projection operator was like given like this, and this xi state is defined like this, times this would be plus a square magnitude of a, because we have evaluated this and it was under square root. This projection operator would go inside, and a, since is a complex number, it would come out of the inner product, and this plus half and plus half would give us 1 as their inner product, and this plus half and minus half are orthogonal, so it would give us 0. So this first term would survive, and that would be, and this ket would come out like this, and this square root of the magnitude of the complex number a would give us simply the magnitude of a phi plus half state. And note, any complex number divided by its magnitude is a complex number which has only its phase and a unit magnitude. Okay, so this thing is nothing but only a phase. So up to n phase, the post measurement state is plus half if we have observed the value h bar by 2 of the spin or sz operator. So this system goes into this state plus h bar by 2 with probability 1. So this means that if you send the upper beam of silver atom again into the Stern-Gerlach apparatus, there would not be a splitting of it because it is in the state plus half with probability 1. So the same can be said for the minus half beam of the silver atom. So next is in classical physics, we never gave a thought to the question whether we can measure the temperature as well as pressure or any other pair of variables simultaneously, because the answer was intuitively obvious, that is, it was yes, we can measure it. But in quantum physics, as most things are, the answer is rather unintuitive. That answer is not always yes. So this brings us to the notion of compatible and incompatible observables. So for your information, in quantum mechanics, the Hermitian operators corresponding to dynamical or physical variables are called observables, So the next topic would be is simultaneous measurement of observables or compatible or incompatible observables and uncertainty relations. So two observables A and B are said to be compatible if they share a common eigenvector or eigenvectors, although their eigenvalues may be different corresponding to the same eigenvector. Or another definition for compatible operator is if two observables A and B are said to be compatible if their commutator vanishes, that is equal to 0. So both of these definitions are equivalent, as can be shown by the following very simple calculation. So let E would be a common eigenvector shared by the observable A and B, or operator A and B. So that means that A operating on E would be equal to some eigenvalue lambda sub A times E, and B operating on E would again be some eigenvalue lambda sub B times E. And if I see the effect of this commutator on this eigenvector E, and this would give us AB. So B is A lambda B is B lambda E. Again, this is since are complex number, and because operator and a scalar always commute, so lambda B can be written like this: lambda B lambda A lambda A lambda B. So this E we can take as common, and the remaining thing is nothing but a commutator between lambda B and lambda A, and they always vanish because two numbers always commute, and this is 0. It means that A and B is equal to 0. This implies that A B is equal to 0. Okay, so both these definitions are equal. So let me explain what is happening here, or what does it mean if our two operators are compatible or their commutator vanishes. So again, if you consider two of these observables A and B and assume for simplicity that they are non-degenerate, that is, every eigenspace has dimension 1, or in simple terms, only one eigenvector corresponding to a given eigenvalue, then the measurement of A on a pure state gives us a result lambda A, and the state collapses into the corresponding eigenstate E according to the projective measurement postulate. And since this is an eigenstate of B as well, so a measurement of B does not change the state and gives us result lambda B. After measurement B, a measurement of A again gives the value lambda with certainty. In other words, the measurement of B does not change the result of A, or the measurement of A doesn't change the measurement of B. So for this reason, commuting observables are called compatible. So going further, we can generalize the measurement postulate for a single observable as discussed earlier for the measurement of several compatible observables. It says that if the state immediately before the measurement is psi, and the results of the measurements are the eigenvalues lambda 1 lambda L of the observables, let's say S1 S2 SL, with projectors corresponding to each eigenvalue be P1 P2 up to PL respectively, then the state after measurement would be given like this: PL minus 1 PL minus 2 up to P1 operating on this high times the norm of this state. The probability of obtaining this L-fold results of lambda 1 up to lambda L is written like this: lambda 1 up to lambda L, probability of obtaining of this L results simultaneously would be this PL minus 1 P1. This is the probability of obtaining this L-fold results. So note that if any two projection operators, their multiplication, it gives us 0, where this Pk and Pj correspond to two eigenvalues lambda k and lambda j, and for the observables Sk and Sj. then obviously that two values lambda k and lambda j cannot appear simultaneously as a result of measurement. And as said earlier, and that probability of occurrence of this event is 0. This is because sk and sj are assumed to be incompatible operators, so they do not share the same set of eigenvectors and cannot be written in terms of same set of projection operator constructed out of the eigenvectors of either of the two operators. Therefore, the output subspaces corresponding to this projection operator pk and pj must not at all overlap, otherwise then the probability of obtaining these two lambda k and lambda j would not necessarily be equal to 0, meaning that there is a finite probability, no matter how small, that by doing measurement we can obtain lambda k and lambda j as results of measurement simultaneously, which is in contradiction of our assumption that sk and sj are incompatible operators. So let us explore further the consequences of the fact that two operators a and b are incompatible. That means mathematically that their commutator is not equal to 0, that they do not vanish. So for a physical state psi, consider the following two states. State f even defined like this: a minus the expectation value times the identity operator times operating on this state psi, and state g is obtained after operating this operator, which is b minus the expectation value of b times the identity operator on psi. These two operators are defined such that the inner product of these two states f gives us the variance of the observable a or the operator a, and g is norm would give us, you can check it by multiplying it, the norm would give us the variance. So the Schwartz inequality immediately furnishes for us an inequality times f times g times norm is obviously this is the Schwartz inequality, which says that if we are taking the inner product of a vector with itself and we interpret it as the length of this vector in the Hilbert space, so the length of these two individual vectors, their multiplication is obviously always greater than or equal to square of this distance of these two vectors in the Hilbert space. Okay, this is what this Schwartz inequality says, which is very intuitive. Now this fg, the inner product in general, is a complex number, and this implies that it must have this square root, this is magnitude square, okay, is same as equal to the is real part whole squared plus this complex number imaginary part whole square. Okay, I think this is clear to you, because magnitude of any complex number is given like the real part squared and the imaginary part square root over it. So since it is square, so the square root vanishes and we only remain with the real and imaginary part square. Okay, as we have obtained defined earlier that this two inner product, these norms are nothing but the variance of these two operators a and b, and we have said that this is the inner product squares of f and g, and this magnitude squared is evaluated like this. So our task is now to compute each of these two terms in the above right hand side, that is these two terms. For convenience of calculation, we introduce these two notation for this operator, and again this as notation for this operator. So now let us calculate this inner product, which is equal to, okay, I hope you getting this, because we have defined f as this times xi and g is there this times xi. Okay, so obviously this is equal to just using the definition of f and g. If you compute this multiplication of these two operator, this would be AB minus A expectation of B times I minus A expectation of A times I times B times A B expectation times I and xi. And if you see xi, this would give us the AB, and since this expectation value is a number, it would come out, and this would remain I operating on the state xi would again give us xi, and this xi and this A would become the expectation value of A. And similarly this one also, and this are both are numbers times the identity operator, which upon operating on this xi would give us xi again, and this would be this xi AB xi. And since these are numbers, both of them are equal, this would be can be written like this. This is, I guess, this was plus, because both of the terms minus A expectation of 8 I minus B expectation, with when they get multiplied they would give us plus. Okay, this would give us A minus, simplifying this would give us this. Similarly you can same for GF, reverse the net product between G and F. So this would be again xi. Compute this, you would get simply the order. If you simply take this complex conjugate of this expression, that would become this. We can now use this to find a nice expression for the imaginary part of the inner product Fg, which is given like this. Imaginary part of this inner product. You know this, I guess, I hope you know this, that the imaginary part of any complex number is the complex number minus the complex conjugate of this complex number 2 times iota. So we have computed both of them, this and this. This would be equal to this psi AB minus BA psi. So obviously this would be equal to psi AB psi BA, and both of us we can write like this, AB minus BA psi. If you note, this is commutative between A and B, so psi commutative between A and B. So this was the imaginary part of this inner product. So for the real part, the expression is not that simple, because the product of expectation value do not cancel, because if you know that this real part is given like this, any complex number, that is this addition of the complex number with its complex conjugate, and because the expectation values won't cancel, this product of expectation values, so we would write the real part as the anti-commutator. Anti-commutator is nothing but the of any operators. AB is nothing is defined like this, AB plus B, not minus. So this is called anti-commutator. Therefore we can write the real part of Fg as this, and we would write this as the anti-commutator between these two operators. If you compute this, you would get this. Putting this expression in we obtained back to the equation, and we obtained from Schwarz inequality, we get and this expression delta the variance of A squared variance of B is greater than equal to the imaginary part of the inner product of f and g, which we have obtained, is equal to this, plus the real part of the inner product between f and g, which we have obtained. So this can be viewed as the most complete form of the uncertainty inequality, This uncertainty means or variance inequality between two Hermitian operators A and B. Okay, it turns out, however, that this second term on the right hand side is seldom simple enough to be of any use, and many times it can be made equal to 0 in applications for certain states. So at any rate, this term is positive. This sum of, so at any rate it is a positive term. Okay, and it can be dropped from the inequality while preserving the inequality. This can be dropped, and yet this side would be less than this side. The inequality is preserved. So the net uncertainty equality between any two Hermitian operators A and B can be written like in a very simple form like this. So this A and B, if as an example, and that too very important, that you know that the commutator between the position operator and the momentum in that direction is given like this, and if you put this thing over here, the variance of the measurement of the position squared and the variance in the measurement of momentum in the same direction as the direction of position is equal to xi. If the system the particle is in the state xi, this would give us iota h bar xi. This iota cancels and this would be same, and LHS would become this. Xi would give us, sorry, this was h bar by 2. The expression of which we have obtained from short is inequality. The imaginary part and real part were squared. Okay, so this is also squared. So this means this is squared. This is also squared. So this h squared by 4 would come out, and this is squared. So this is, so our net inequality would become the variance of, this is the famous Heisenberg uncertainty principle. The purpose of this discussion of this theory of incompatible operator was to show you how a mathematical property leads to consequences on experiments, that you cannot measure two incompatible operators simultaneously precisely. That is, if you want to measure one precisely, the other one's uncertainty or variance increases. So that's it. Next topic would be, so it must be clear to you by now that the quantum theory predicts statistical quantities of an experiment, not the outcome of an instance of experimental measurement. By the theory of probability, we note that the statistical quantities like the expectation value and variance depends on the underlying probability distribution. This suggests that quantum theory should predict the probability distribution one would obtain in the experiment. This fact you already know but was not talked about explicitly. You also know that any normal operator can be written as linear combination of projection operator. Any normal operator m hat can be written as linear combination, which is the result of the spectral theorem, or this is for an operator which has discrete spectrum, that is has non-continuous discrete eigenvalues, and m hat for continuous spectrum is just an integral and dpm. So this is an operator, and you can think dpm as via that the expectation value of dpm is the elemental probability. Okay, so this is it, and the probability of observation eigenvalue m of the operator m hat, as mentioned in the postulate 4 of the projective measurement postulate, is given like this. So where pm is the projection operator corresponding to this eigenvalue m. I take m as a variable, and we can then this pm can be interpreted as cumulative distribution function of a random variable m and corresponding to an Hermitian operator m hat. and treating the eigenvalues of it as the values of this random variable n. The purpose of discussing all of this was to revisit the postulate 1 and ask what actually normalized state vector xi in the Hilbert space is modeling about the actual physical quantum mechanical system. This will allow us to make contact with actual experimental situation which go beyond the normalized state vector in the Hilbert space model. Okay, we know that if we want to estimate the statistical quantities through experiment, we need large collection of samples, not a single sample. So any quantum mechanical experimentalist prepare a large collection of quantum system prepared in a specified set of experimental condition, and these set of experimental condition, at least in principle, can be realized in infinite number of times. The collection of these quantum systems in physics text are called ensembles. So therefore, consider the statistical ensemble written in calligraphic E consisting of large identically prepared quantum systems. Let us denote like this: S1, S2 and up to Sn, and each is a realization of aforementioned identical set of experimental condition. Now what the first postulate says that under certain condition a complete characterization of such a statistical ensemble is provided by a normalized state vector xi. That is, this ensemble or the collection of quantum systems S1, S2 and Sn, this ensemble is completely characterized by the state vector xi in the Hilbert space pertaining to this quantum mechanical system. It means that we have prepared all this n quantum systems are in the state xi. Okay, because they were prepared in a similar or identical set of experimental conditions. But still our characterization of quantum statistical ensembles is not yet the most general one encountered in application of quantum theory. So an obvious way to obtain more general ensemble is the following. So if you consider this diagram, if you have lot of ensembles, epsilon 1 and epsilon 2 and epsilon, if you have m number of ensembles and they are prepared in different set of experimental conditions, that if this collection of quantum systems were prepared in some kind of experimental conditions, and this E2 is ensemble 2 is in some other set of experimental conditions, and similarly up to m. Okay, and therefore the epsilon 1 can be characterized by this state xi1, normalized state vector xi1, and this is a xi2 up to xim. That is, all the quantum systems in this ensemble are in the state xi1, xi2 and xim. And let us mix this in a separate ensemble is epsilon, or separate bag of quantum system. We form this ensemble or bag by taking n1 number of from this ensemble epsilon 1, n2 number of quantum system from this ensemble epsilon 2, and m number of systems from this ensemble epsilon em. So this is not an epsilon, it is e. We have created this ensemble epsilon. This is a mixed ensemble because it is not completely characterized by a single state vector, because some quantum systems are in the state xi1, some are in xi2, some are in xim. So we cannot have a state vector characterizing this ensemble. Okay, so another thing is that this n1 plus n2 and n are up to n3 up to nm r is n. So we have n number of systems, n number of quantum systems in this ensemble. So alpha is some index varying from 1 to m. So we have written like this expression like this as a summation. So this allows us to define another quantity W alpha, which characterizes the fraction of these quantum systems taken from the ensemble epsilon alpha, where alpha can be 1, 2, fraction of systems in the ensemble E if taken from the ensemble E alpha. These are called weights W alpha, and I hope you are getting this, how we have obtained this ensemble, this collection of quantum systems E from these ensembles epsilon 1, epsilon 2 and epsilon m. Okay, then the cumulative distribution function for this type of ensemble for a given observable represented as by some Hermitian operator r hat, which corresponds to some random variable r. That is, this cumulative distribution function for the and is given like this. You know the probability that we obtain this eigenvalue small r if my system is in the pure state psi alpha. Okay, this was the probability, and this is the projection operator. I have changed the notation from P to E. It would be clear in the later lectures, and that is when we deal with generalized measurement, we would denote the measurement operator as ER as opposed to this projection operator. Okay, then in the generalized measurement case, this projective measurement becomes a special case. So it is, this notation is aligned with the generalized measurement, which would be dealt in the later lectures. So for now you can understand this as this projection operator that I have defined in the earlier class. So this was, if you remember, was the probability that we would get this small r as the value of measurement of this operator r hat, and since not all quantum systems are in this state psi alpha, so we have to multiply this probability with the fraction of the systems which are in the state psi alpha or taken from the ensemble epsilon alpha. Okay, so that would be W of alpha. So again, this is the complete probability that if we measure the W alpha fraction of the system which are in the state psi alpha, we would get this small r as the value of measurement. So, and since we have a lot of quantum systems which are in other states other than psi of alpha, we have to sum it over the alpha, which can vary from 1 to n. So this is the complete and most general expression and of cumulative distribution function as predicted by the quantum theory. Okay, this ER is sometimes denoted as taken from the set of spectrum of R hat. Okay, so ER belongs to the set of subspaces corresponding to each eigenvalue of R hat. It is nothing but generalized form of this projection operator, which would be dealt in the later lectures, when in the lecture for generalized measurement. So for now you can understand it by the projective operator as a projection operator. Okay, so this equation generalizes the previous cumulative distribution function for pure ensemble, that is the ensemble of quantum systems which are in a single state of psi. That's sometimes I refer to as a pure ensemble, because it is all the systems are in a single state. Okay, so the expectation value of any random variable or corresponding to some operator r hat is again written as the expectation value of the operator r hat for the systems in the state xi alpha times the fraction of the systems which are in the state xi alpha and summing over all the possible states which are 1 to m, all the ensembles. So this would be the expectation value. So the statistical formulae, that is this expectation value and the expression for this cumulative distribution function, can be cast into a compact form by introducing the density matrix or statistical operator, which is given like this. So the distribution function then can be written as trace of ER with rho. Okay, this is ER is W alpha. This is given like this. Okay, so this W alpha can be taken out and the trace of this operator can be given like this. Since inside a trace we can obviously cyclic rotation is allowed of operators, and the trace of this would be the summation alpha. So define the so because if just for refreshing of memory, trace of any operator was defined as where the set of state phi i's are orthonormal basis for the Hilbert space H. This is what we have used over here. Okay, from obtaining here to there. So this is what our trace would be, and we have shown that this trace is a basis independent property of an operator. So this expectation value or therefore would be given as this r hat rho, and variance is expectation of r squared minus expectation of r whole square. So this is trace. One thing I have to clear, that this xi alpha is assumed to be forming the basis for the Hilbert space corresponding to the ensemble E alpha, okay, which is characterized by the state xi alpha, and it has an underlying Hilbert space obviously. So and this xi alpha state span this Hilbert space. So the trace of this ER times this is nothing, summation like this, which is the definition of trace, or you can say the diagonal elements of the matrix corresponding to this operator ER. So I hope this is clear, there is no confusion relating to it. So this would be it, and this is just the introduction for this density operator or the statistical operator. In the next class I will be dealing with some properties of this density matrix, and I would convince you also that this, interestingly, this operator forms a state vector in the Hilbert space. Okay, so and we will reformulate entire quantum mechanics using this statistical operator, that is serve the same purpose as a state vector xi in the new formulated quantum mechanics using this state vector rho. And because it also models very easily the experimental situations where my collection of quantum systems are not in a pure state, that is some systems are in state xi1 or some state are in state xi2, or fraction of quantum systems are in state xi3 and so on. So it completely characterizes that or that situation also. So it is more general than the state vector xi in the Hilbert space, okay, which can be used to characterize a ensemble which has all the quantum systems are in a single state xi. So that would be it in today's class. Okay, so see you in this next class, guys. I hope you enjoyed this class today. So bye.